Okay, everybody, welcome back. You are to be congratulated as a group. I looked at the test scores, and the median score was like 90%, which is like I've never really seen that before. So, well done overall. I realize that some of you may not have done as well as you wanted to have done, and after class, you should be able to see the items you missed, what your responses were, and what the correct answers are on the Testing Center website. I'm also going to make a video like I've done in the past where we go through each question. All right. Oh, and I think there's probably a worry among students when you hear that a exam median score is that high that somehow I'm going to be wringing my hands in my office saying to myself, dang it, they did too well, and plotting ways to get my revenge on you. That isn't true. Also, some people are afraid, oh, well, now if everybody did well in the class, that means that it's going to be even harder to get an A, and that is also not true. As I said at the beginning of class, it will never be harder to get an A minus than to earn 90% of the points. It will never be harder to get an A than earning 93% of the points, and so on. So it's not like we say, ha ha, the joke's on you, the A is 97 and above. That's not what we're going to do. Okay. So we have been talking about metabolism, and we started with the fatty acids, or rather with triglycerides. We talked about how after you hydrolyze the triglyceride, glycerol gets modified by ATP to make a phosphoester, and then we oxidize carbon 2 to make dihydroxyacetone phosphate, which goes to glycolysis. Then we talked about what happens to the fatty acid. To prepare it for beta oxidation, we first have to turn the carboxylate, turn the negatively charged oxygen of the carboxylic acid into a decent leaving group. And the way we do this is first by having that oxygen attack the alpha phosphorus of ATP, pyrophosphates the leaving group, and that goes on and gets hydrolyzed to provide a driving force for the reaction. And then you end up with this linkage, which is not really an anhydride, not really a phosphoanhydride. It's like half of each. But this is adenosine monophosphate, AMP, is a good leaving group. And so in the next step, we're going to replace the AMP leaving group with this coenzyme A, thiol. Now, I haven't said what coenzyme A is. I can show you the structure at some point. All you need to know right now is that it's got a sulfur, a thiol sulfur on it, and thiols are good nucleophiles. So a base will remove a proton from coenzyme A's thiol, and then that thiolate, negatively charged sulfur, will attack the carbonyl carbon to get a tetrahedral intermediate. I haven't shown you the rest of it. It's basically nucleophilic acyl substitution. Electrons kick down, AMP leaving group leaves, and you end up with this thioester. Okay, that's what we did last time. The reason we want a thioester is because our goal is ultimately to clip units of acetyl-CoA off of the fatty acid. And so we're going to need the CoA thioester here. And then our other goal is we want to make the process iterative. So when we're done, when we have clipped off acetyl-CoA, we want the other portion of our molecule to be ready to go right back to the beginning again. So we talked last time about the first two steps of fatty acid beta oxidation. We looked at the fatty acid thioester. We noticed that if we want to clip off a 2-carbon unit here, the 2-carbon unit would include the carbonyl carbon and the alpha carbon, but we can't do that yet because the bond, if we were thinking about breaking this bond between alpha and beta carbons relative to a carbonyl, we might be thinking of some kind of carbonyl enolate chemistry like the aldol or the Claisen reaction. But in both of those cases, we would need some kind of oxygen on the beta carbon. And here we've got nothing. So our first step is going to be to oxidize the beta carbon. And the way we do this involves a mechanism that I showed you last time. We first remove a proton from the alpha carbon to make an enolate. And then that enolate electrons will kick down and you can actually show this a couple of different ways. It's maybe easiest to draw the enolate like this. That's just another resonance structure, the enolate. Electrons on the alpha carbon kick down, and we want hydride to be our leaving group. Of course, hydride is a terrible leaving group, but it never actually leaves on its own. In fact, it's as it leaves, it's received into this portion of the molecule FAD, which is an oxidizing agent. This nitrogen's electrophilic. You don't need to worry about why. We talked about how it's conjugated to electron withdrawing groups like these carbonyls and carbonyl oxygens. So hydride gets delivered here, and electrons shift around, and we also pick up a proton in another part of the molecule to deal with the resulting negative charge. And when we're done, we have this alpha-beta unsaturated thioester. Okay? Sort of, yeah? Okay. FADH2 is the reduced form of FAD, and here's the two hydrogens. This was the hydride, and this was the one that we picked up from some acid at that stage. Now we're cooking, because we now have a double bond between alpha and beta carbons. If a product was an alpha-beta unsaturated carbonyl compound, what was the reaction you used to get it? Remember? Aldol, right? So, but I thought the aldol product was a beta hydroxycarbonyl compound. So where's the OH, and where did this double bond come from? If in an aldol reaction, you can also do the dehydration step afterwards. Remember, where you remove a proton from the alpha carbon to make an enolate, and then that enolate kicks down and the OH group leaves, right? So we might recognize this alpha-beta unsaturated thioester as a potential aldol product. And that should be, I guess, moderately exciting, because that's the aldol, a retroaldol reaction could then break the bond between alpha and beta carbons. Okay. So step 2 is to actually go backwards and install the oxygen at the beta carbon to get the beta hydroxycarbonyl compound. And we're going to do that via exactly the reverse of the dehydration reaction. We're going to call this conjugate addition, or like a Michael addition of OH minus. And remember that beta carbons on alpha-beta unsaturated carbonyl compounds are electrophilic both at the carbonyl carbon and at the beta carbon. And the reason they're electrophilic at the beta carbon is, first, there's LUMO on the beta carbon. This is a conjugated system, and so some of the empty extended pi orbital is on this beta carbon, but also because you can draw a resonance structure where you would put a positive charge on the beta carbon and a negative charge either on alpha or out on the carbonyl oxygen. So it's totally reasonable for a negatively charged oxygen to attack at the beta carbon to give us this intermediate. And then we will pick up a proton from some source, probably from the thing that deprotonated water to give us the OH minus group. All right, so this step is catalyzed by an enzyme called enoyl-CoA hydratase. And the product is this beta hydroxy thioester. Enzymes are often named by what they do. Sometimes they're named for the forward reaction, sometimes they're named for the reverse reaction. For example, this oxidation step above where we made the double bond is catalyzed by a dehydrogenase enzyme. And what got dehydrogenated, why the starting material did, where did those hydrogens go? Here in FAD. Similarly here, we're basically adding water, OH minus, and then this proton. So we basically added water across this double bond. Okay? And this is one of the reasons why we call this beta oxidation. Now we've got an oxygen on the beta carbon. Now, what nature does next might seem, I guess, unnecessary at first, because already we now have an aldol product that we could break apart into its component starting materials by a proposed retroaldol reaction. So let's just think about what the products of that retroaldol reaction would be. Remember that a forwards aldol reaction involves a nucleophilic portion, which is always an enolate, and then an electrophilic portion, which is either an aldehyde or a ketone. So what would be, if we did the retroaldol reaction, what would be over here on the sort of nucleophile side? Acetyl-CoA, but as an enolate. Good. Okay, good. And that will have accomplished one of our goals, which was to clip off a 2-carbon unit as acetyl-CoA. So goal number 1, check. What would the electrophile have been? You can tell what it is by looking at the beta carbon. In an aldol reaction, the beta carbon has an OH group. If that beta carbon is attached to one other carbon and a hydrogen, that the electrophile will have been an aldehyde. If it were attached to 2 carbons, it would have been a ketone. Okay. So what about goal number 2, which was, as you recall, making the process iterative? The challenge we have is I have clipped off acetyl-CoA, basically, but here I'm left with an aldehyde, and the starting material for this process is actually a fatty acid thioester. So in some ways this is inefficient because what am I going to do now with this aldehyde? And there would be ways around it, though, so you can sort of wonder about why nature does things this way. But the problem we're dealing with is that the aldehyde isn't a thioester. And if we can modify the process easily so that the product of that retro step would have been a thioester, then we won't have as much, then we'll be able to move on and make the process iterative without any further modifications. Okay, so we're not going to do the proposed retroaldol. Instead, we're going to use another oxidation reaction to convert the beta hydroxythioester, oops, spoiler alert, to convert the beta hydroxythioester into a beta ketothioester. That's an oxidation reaction. You're going to use NAD as the oxidizing agent, and you're going to get NADH, and you'll need to remove a proton also for this to happen. Basically, that proton is the one that gets removed by a base, and then this is the hydride that gets delivered to NAD+. I'm not going to show the mechanism of this reaction because you've seen it. You've seen something similar before. Basically, you'll have a base, remove this proton, electrons will kick down to make the carbonyl, and then hydride will be delivered to NAD+. That's the part I'm not drawing because we did something similar last time. All right, now you've got a beta ketothioester, and that is a Claisen product. So we could think about proposing a retro-Claisen reaction. Just to refresh your memory, in a Claisen reaction, you take an ester and an enolate of that ester. You have the enolate attack the carbonyl carbon to give you a tetrahedral intermediate. So far, this is exactly like the aldol reaction, only here we have a good leaving group, at least a decent leaving group relative to a negatively charged oxygen. And that's where we get electrons kick down from the oxygen, kick off the leaving group, and we make, ester. Okay, and if we were to think backwards, what would the backwards retro-Claisen look like? We would simply have that negatively charged oxygen attack the carbonyl carbon to get the same intermediate we just drew. Only this time, instead of electrons on the oxygen kicking down to kick off the OR minus group, they're going to kick off the enolate. Okay, so in step 4, if I want to do a retro-Claisen reaction, what do I want to attack the beta carbon? My goal is to have a thioester, so what should be something that's attacking the beta carbon? Could it be the coenzyme A thiol? Ultimately, that's what we want to have at that position. It turns out that the process is a little bit more complicated than that because there's some enzyme-bound intermediates, which I just as well show you, because it gives you another example of what the side chains are doing. So I'm redrawing the beta ketoester, and I realize I'm being sloppy about where I start to say the R group is. That won't matter really for our discussion. So the active site of this enzyme, and it's called ketoacyl thiolase, has a histidine amino acid, and I know you know that structure now. This happens to be at position 375 of this enzyme. There's a nearby cysteine residue, and histidine is going to remove a proton from cysteine, and then that cysteine thiol is going to attack the beta carbon of our beta ketothioester. It's possible that this deprotonation will make you feel uncomfortable because the pKa of the cysteine thiol is 8, whereas the pKa of the conjugate acid of histidine is 6. So that would seem to be a little bit uphill in energy by a factor of 100. But I remind you that these pKa's are measured in dilute aqueous solution, and enzyme active sites are not dilute aqueous solution. They're much more nonpolar than just regular water, and that can change the pKa's. So what we get at that stage, after cysteine attacks the carbonyl carbon, we get the tetrahedral intermediate. And here's where we're going to do that retroclason step. We're going to kick off acetyl-CoA as an enolate. And notice what that leaves me with on the left-hand side. This now leaves me with a thioester here, and then an enolate here. And of course, this can pick up a proton from some source and become regular acetyl-CoA, which is off to the citric acid cycle. Okay, so that's goal number 1 accomplished. Now, goal number 2 is to make the process iterative. So what we do at this stage is to have coenzyme A with its thiol come into the active site. It gets deprotonated, and then we're going to do a reaction that's called thioester exchange. This is basically nucleophilic acyl substitution. The CoA thiol will attack the carbonyl carbon of your thioester to give you this intermediate. And then electrons will kick down and we will kick off the cysteine thiol. And that will give us our fatty acid that has been truncated by 2 carbons. And we're going to take this back to step 1 of fatty acid beta oxidation. What happens to the cysteine that gets kicked off as a leaving group? Well, now it's going to, it's going to steal its proton back from histidine, and that will reset the catalytic cycle, and we're ready to go for a new molecule of beta ketoester whenever that forms. Okay, so that's kind of messy. The summary of the reaction is that we get as products here acetyl-CoA, and then we get a truncated fatty acid thioester, and we get that by bringing in coenzyme A as a nucleophile. Okay, questions about that? Yeah?
Is there a reason you can't just use coenzyme A with the thiol? Why is that?
Is there a reason you can't use coenzyme A as the thiol straight from the beginning? Great question. I don't know. I do know that when you make one thioester, then thioester exchange is pretty rapid, and so it's likely a practical issue. Imagine the enzyme has to first the the beta ketothioester has to find its way randomly to the enzyme active site. It's unlikely that that would happen at the same time as a molecule of acetyl-CoA found its way randomly to the active site. So likely, I mean, I'm just guessing here in terms of the kinetics, but it would seem reasonable that the beta ketothioester would come in first and get bound by the enzyme and activated, and then acetyl-CoA, or then the CoA thiol would come in and bind. So probably it's just an issue of it's easier to get two things together than to just get one thing, than to get, easier for two things to find each other than for three things to find each other randomly. Okay, what else? Yeah?
Does this process happen with just the saturated fats or also the unsaturated?
Yeah, great question. It happens with the unsaturated fats as well. The question is, how would it be different? If the double bond is in the right place, you might be able to skip this first oxidation step and go straight to the addition of water on the beta carbon. If it's in the wrong place, you probably have to reduce the double bond first and then proceed. So I'm not sure actually what nature does, but ultimately everything gets shunted down this pathway. What else? So hopefully you can see that by doing this, we clip off a 2-carbon unit of acetyl-CoA and we're left with this thioester. That goes back and it continues to cycle through until we've gotten rid of all of the carbons of the fatty acid as acetyl-CoA. That means also, incidentally, that the starting material from this reaction needs to have an even number of carbons, and that's true for almost all of the biological fatty acids, because fatty acid synthesis occurs in basically the same way as this beta oxidation occurs, but backwards. It's a different enzyme machinery, different thiols are used, but basically to make a fatty acid, you start out with 2 molecules of acetyl-CoA, you do a Claisen reaction, you reduce to the alcohol, you eliminate to the alpha-beta unsaturated thioester, then you reduce the thioester to the just regular alkene, and then you've got your fatty acid. You continue to iterate that process as well to get as long as you want, but each unit that comes in is only 2 carbons long. Yeah? Say that again, sorry? Oh, what title would I give step 4? Oh, sure, retroaldol. No? Is that? Yes, that's right. Retroaldol reaction. Okay, so that's fatty acid metabolism down to acetyl-CoA, which goes to the citric acid cycle, and we will get there. But we're going to pause and step over to the world of carbohydrate metabolism, because you'll see that that process also intersects this one at acetyl-CoA. All right. Any more questions, though? Any other issues you want to ask about fatty acid metabolism? Okay. Right, so carbohydrate metabolism begins in the cytosol with a process called glycolysis. Lysis means to break, so glycolysis is breaking apart sugar. Glyco is sugar, lysis is to break. Overall, let me give you a sense for what happens in this process. We're going to take glucose, beta D-glucopyranose, or just D-glucopyranose to be precise. Don't care whether it's alpha or beta anomers. This is C6H12O6. We're going to take 2 ADPs, 2 phosphate molecules, which I'm abbreviating like that, 2 NAD pluses, and 2 water molecules just to balance things out. You didn't think you'd be balancing equations, and you're not actually. I'm going to do it for you, but and you don't have to memorize this. I just want to show you the overall transformation. Pyruvate is this 3-carbon alpha keto carboxylic acid, and its formula is C3H4O3. In doing this, we'll make 2 molecules of ATP, 2 molecules of NADH, and we'll have 2 spare protons as hydronium. So you can see why this process is called glycolysis, because we break the glucose into 2 pieces. And we break it into 2 of the same pieces, which is going to define a lot of the initial steps of this process. So glycolysis has a couple, two different phases. The first is the investment phase, and we're actually going to consume some ATP in this phase. But it's not a Ponzi scheme, which means that we're going to make that back and some additional ATP. So what I've written here is the net benefit in terms of ATP. NADH can be taken to the electron transport chain. Each molecule of NADH can lead to, oh shoot, I forget what the conversion factor is. I wrote it down here somewhere, but I can't think of it now. It's something like 2 or 3 molecules of ATP for every equivalent of NADH in the electron transport chain, which can then go to drive more, So let's begin with the investment phase. This is going to involve preparation of glucose to be broken apart into 2 similar things. And you've actually seen that breaking apart into 2 similar things in a retroaldol reaction on exam 2. The first step involves taking the glucose molecule. At this stage in talking about glycolysis, people usually don't specify whether it's the alpha or beta anomer. They also, I guess, to be short in writing and talking, dropped the whole beta D-glucopyranose thing, and we'll just understand that we'll call that glucose. We'll understand that it could exist as alpha and beta anomers. We'll understand that it can exist in this pyranose form. We'll understand that it has a open chain form, and we'll understand what the stereochemistry is at carbon number 5. That's D stereochemistry, but we won't worry about specifying it. So the enzyme that catalyzes this reaction is called hexokinase, which means we're going to be doing a phosphorylation. ATP, we use ATP to make a phosphoester with this OH group on carbon 6. And you've seen that kind of thing before. The mechanism is basically an SN2-like mechanism. We'll remove a proton from oxygen. We'll have oxygen attack the gamma phosphorus of ATP, and then ADP leaves as a leaving group. When we're done, what do we have? We've got a phosphoester. And then ADP. The molecule here is called glucose 6-phosphate because the phosphate group's on the OH on carbon 6. This reaction is really downhill in energy. The change in free energy for this reaction is like minus 8.1 kilocalories per mole. And that is essentially irreversible. You will hear different numbers quoted for whether or not, or for these free energy numbers for these reactions. What they are depends on what your standard state is and whether you mean to be talking about physiologically relevant concentrations of starting materials and products and so on. But the idea is that this is really downhill in energy. The reason it's downhill in energy is because the bond we're breaking in ATP is a phosphoanhydride bond. And the bond we replace it with is a phosphoester bond. Now, it's a decent time to talk about a misconception that I think I've alluded to previously. Sometimes in various classes or science experiences you've had previously, you may come up with the idea that ATP is the body's energy molecule. It's energy rich, and it is. But you may come up with the idea that breaking apart ATP releases energy. And that is not technically true. It's shorthand, and I can see what people are doing, but it's not technically true. Breaking a bond requires energy. That's uphill. Making a bond releases energy. So when a reaction is favorable like this, is downhill in free energy, that must mean that the bonds you form are stronger than the bonds you broke. And that makes sense. The ATP, I can find an example of that. The phosphoanhydride bond in ATP is like a carbon anhydride, and the phosphoester bond in glucose 6-phosphate is like a regular carboxylate ester. Just as anhydrides are less stable than esters, so phosphoanhydrides are less stable than phosphoesters. Okay? Just understand that. Don't ever tell anybody in the future that you think ATP breaking apart releases energy, because that will drive me crazy. And even if you do it when I'm dead, I will be hovering and haunting you for so saying. Beware. Okay. So the next step is an isomerization reaction. It is the enzyme that catalyzes this step is called glucose 6-phosphate isomerase. Guess what this enzyme does? It isomerizes stuff, right? So we're going to take glucose 6-phosphate. I'll abbreviate that phosphate group. Oops. And we're going to turn it into fructose 6-phosphate. Oh, wow, that's terrible. Sorry about the penmanship there. I guess I'm sorry, but not sorry enough to change. So fructose 6-phosphate exists in a 5-membered ring form, which I'm going to attempt to draw. Maybe. Oh, no, there it is. That's a 3. All right, let me number the carbons of both of these so that you can see what ends up where. 1, 2, 3, 4, 5, and 6. Similarly, 1, 2, 3, 4, 5, and 6. If you compare each of these carbons, especially 4 and 3, the stereochemistry is the same, right? On carbon 4, the OH group is down, same thing over here. On carbon 3, the OH group is up, same thing here. We don't tend to worry about what the actual conformation of a 5-membered ring is because they're pretty flexible and don't stay in one for very long. So that's why I haven't really attempted to show this in any sort of reasonable shape. One thing to notice about the starting material and the products is that the anomeric carbon is a different carbon in each structure, right? So this is glucose, and the anomeric carbon is carbon 1. In fructose, the anomeric carbon is carbon 2. So that's part of the isomerization. You can see it a little bit more clearly if you draw the open chain form of both of these carbohydrates. Glucose is an aldehyde. In contrast, fructose is a ketone. And again, let's number the carbons just so we can keep track of everything. 1, 2, 3, 4, 5, and 6. 1, 2, 3, 4, 5, and 6. All right, so it looks like we've done a reduction reaction on carbon 1 because we've got a primary, or we've got an aldehyde that we convert into a primary alcohol. So that looks like, oh, sodium borohydride reduction. Of course, nature doesn't use sodium borohydride, but we could do that with NADH. But on carbon 2, it looks like we've done an oxidation reaction because we convert a secondary alcohol into a ketone. So in the same molecule, you've got oxidation and reduction. It means you can actually do this without using any redox reagents at all. In fact, we can convert from glucose into fructose through 2 different tautomerization steps. Now, remember, tautomerization was where we would take the keto form of an aldehyde or a ketone and turn it into the enol form. That involves moving a proton and moving where a pi bond is. So if we were to tautomerize this aldehyde, we would take the hydrogen on carbon 2, we would have some base remove the proton, and that would give us an enolate intermediate. Oops. And then we can, of course, that enolates negatively charged on the alpha carbon and on the carbonyl oxygen. So tautomerization would involve us protonating the carbonyl oxygen with some acid, probably the conjugate acid of our base. And that will generate, sorry, the following enol. Okay, here is an enol, and all we've done is we've changed where a double bond is, and we've changed where a hydrogen is. Okay, but if you've noticed, it's not just a regular enol, it's an enediol. And what that means is, we can look at this enol from the pink perspective where this is the carbonyl oxygen, this is the carbon, and this is the alpha carbon. Or we could look at things from the orange perspective. That's not orange, that's sort of yellow. Where this is the carbonyl oxygen, this is the carbonyl carbon, and that's the alpha carbon. This is sort of a double enol, or what we might call an enediol. And that intermediate now makes it possible for us to go through another tautomerization step to get a different product. If, of course, at this stage a base removed the pink proton and went back to the enolate, we could go back to the glucose aldehyde and that would be fine. If instead the base removed the hydrogen, remove the proton, remove the yellow hydrogen, we would get a new enolate. Okay, and then we can pick up a proton on that on the alpha carbon. Oh, that's miserably terrible to read. Alpha carbon. Electrons kick down, pick up a proton from some source, probably the conjugate acid of our base. And that then gives us the new ketone. Okay? Whereas before the aldehyde was here and the alpha proton was there, after this process the double bond is there and the proton is there. So 2 tautomerization steps. Okay? So this is why we made you practice tautomerization so many times over the course of this class and in 351, because this is a really efficient way to move a carbonyl around if you have an OH group on the alpha carbon. Now we should just say something about strategy. What is the purpose of going from glucose to fructose? Remember what I said at the beginning, glycolysis, that's cutting sugars in half apart, and the process cuts a 6-carbon sugar into 2 identical 3-carbon pieces. So we need at some point a reaction that breaks the molecule into 2 3-carbon pieces. In glucose, you could envision doing a retroaldol reaction because, behold, a beta-hydroxycarbonyl compound. That's an aldol product, and you could do a retroaldol reaction to break this bond. Problem with that is that would break the molecule into 1 2-carbon piece and then 1 4-carbon piece. And then you would need different enzymatic machinery to deal with those 2 pieces, and that's not efficient. So if we wanted to instead break the bond between 3 and 4, 4's got an OH group too, so the retroaldol is a possibility, but we got to get a ketone on carbon 2. Notice how over with fructose, once we have the ketone on carbon 2, 3 is now the alpha carbon and 4 is the beta carbon. It is a beta hydroxy carbonyl compound, so we can break it apart via a retroaldol to 2 3-carbon pieces. And then if those 2 3-carbon pieces are similar enough, we can use the same machinery to deal with them downstream. Okay, so there's this process makes good chemical sense. I mean, there's good chemical logic to this process, and what you've learned so far in 351 and 352 should help you to sort of see why it needs to be this way. All right, we'll just stop there. Have a fantastic Friday and great weekend. I'll see you Monday.